This is Unit 12, Lesson 6, Line and Curve Regression. The first thing we're going to talk about in this video is the correlation of linear data. Remember, data that is linear will be in a straight line direction. So it could be in a straight line with a positive slope, straight line with a negative slope, or it could have no correlation at all, where the data is just scattered all over your graph. So you're going to have an exercise to do, and they're going to ask you to choose which of these correlation the graph is indicating. So it could have a strong positive or negative correlation, which you can tell it's in a positive direction. Positive is this direction. Remember, negative is in this direction. It could be a perfect positive or negative direction, meaning all of the data would lie on one individual line. If that happens, this is said to be a perfect positive or negative correlation. It could have a very weak positive or negative correlation. That's where the data is more spread out, but you can see that it's definitely in a positive direction or a basic negative direction. And then it could have no correlation at all, which means the data points are spread all over and you can't see where there would be any line that you could draw to indicate any kind of measurement. So here I have just three simple examples. If you look at this one, you can tell that this has a negative correlation because you could draw a negative line between all of those data points somewhere and get a good estimate of where the actual line of regression would be. And I would say that this one would be a strong negative correlation. For this one, it looks like the data points are everywhere. I can't see any line that would be going toward the left or up toward the right. So I don't see any way we could tell that this is any kind of correlation at all. So we would say no correlation for this one. And then for this one, you can see that you can draw a positive line and it would lie on every single point on this. So I would say that this is a perfect positive correlation. As far as a weak positive or negative correlation would go, you would definitely be able to tell that the data is going in a specific direction, but the data might be more spread out than what something like this is. And with these type of examples, you're just going to have a drop-down menu where you can choose which of these 7 categories it would fall. The next thing you're going to have to do in this section is identify different types of functions that we've learned throughout the year. And I have listed here all of the functions that we have talked about at some point in the year. So in the next slide, I'm just going to show you real quick graphs of each of these because that's what you're going to have to do, is identify which type of function you have on the graph. So just to draw some real quick linear equations. A linear equation is an equation that is a straight line. It could go up toward the right or it could go up toward the left. Either way, it could be a straight line anywhere within the graph. It could be going through the origin, but remember, if it goes through the origin, it could also be considered a direct variation. So let me just go ahead and do direct variation. If it's a direct variation equation, it will have to go directly through the origin. If it's a constant function, it will be a function that is a horizontal line, and it could be a horizontal line anywhere within that function. If it's quadratic, it will be a parabola either facing up or it will be facing down. If it's cubic, it will have 2 curves. Remember, cubic functions have an x cubed in them. So if it's an x cubed function, then it's going to have 2 curves. It's going to have 3 roots. It could cross the x-axis in 3 places, or it could have some imaginary roots like this one would. Remember, anywhere it has that little cusp, but it doesn't cross the x-axis, we have imaginary roots right there. This is considered a cubic function because it has the 2 curves right here. And cubic functions, since they are odd powers, will open in different directions or will point in opposite directions. So this one is going down toward the left and up toward the right. This is also a cubic function, up toward the left, down toward the right. They could be facing in either direction. If it's a quartic function, quartic functions have a 4th power of x somewhere in them. And if it's quartic, since it's a 4th power, they will both either be facing up or down for your end behavior, and you will have 3 curves. Remember, the number of curves is 1 less than the degree. So a quartic function could look something like this. It might look something like this. If it's a logarithmic function, the equation will have a log or a natural log within the function, And remember, natural log functions have this basic shape. Natural log functions look very similar to square root functions, but they do continue on forever in both directions. They will usually hug a vertical asymptote somewhere on the graph, but then continue in a looking similar to a square root function, but continuing forever in both directions. Now let's talk about the difference between a square root function and a logarithmic function. In a square root function, you will have a specific point where the square root function begins, and then it will go on forever in the other direction. This would also be considered a square root function, but it does definitely end at the point where it begins. Okay, so it does not go on forever in both directions like the logarithmic would. If it's an exponential function, remember, exponential functions start out having a horizontal asymptote, and then they get very, very big very, very quickly. So they go up or down exponentially. For a piecewise function, you might have a portion of the graph that goes down like this. You might have another portion of the graph that does something like that, and they do not necessarily touch each other. There are all different sorts of piecewise functions. You could have something like that. That would be considered piecewise. You could have something like this, and that's considered piecewise. So piecewise functions will be a bunch of different portions of a graph, either connected or not connected to each other. If it's a rational function, we will have some asymptotes somewhere a lot of times. So like I might have an asymptote here. And remember, asymptotes may not be shown on the graph. So a rational function could look something like this, where it's going to approach your asymptotes on either side. You could have something like this, where you have 3 different portions of your graph. Or you could have something like this. You could have something that looks linear, but then in the middle of that linear function or that line, you have a hole in the graph. Remember, holes in the graph have to be rational. Direct variation, we said would go through the origin and be a straight line. Inverse or indirect variation, now that's very similar to rational functions, so you have to be real careful there. In an inverse or indirect variation function, your x and y axis will be asymptotes. It will be something in this direction. So you could have the first and third quadrant with portions of the graph. You could have the second and fourth quadrant with portions of the graph. Or you could have any portion of the graph. Like I could have a graph that just has that, and that could be considered an inverse variation. I could have a graph that just has this, and it would be considered an inverse variation. So you could have any one of these in one graph, and it be considered inverse variation. And then for absolute value functions, your absolute value functions will be a V shaped somewhere on the graph. So that's pretty much it for identifying what a function looks like. Most of these will be matching type problems where you just have to match the best graph with its answer. And just make sure that if it has a possible, like if it's linear and could be linear or direct variation, just make sure you're choosing the correct one or the best answer. For constant functions, they would never be considered linear. They have to be constant. You have to say that they're constant because they're horizontal. For direct variation, they have to go through the origin. If they don't, then they would be considered linear, not direct variation. For absolute value, they have to have a V. For square root and logarithmic functions go forever in both directions, but square root functions do not. So those little things you have to understand within them. Here it says identify the type of function graphed in each image below. Okay, this one, it goes through the origin and it is linear. So we could say that this one is linear, or we could say that it's direct variation. For this one, that is a straight line. We don't want to say that it's linear. The best name for that would be a constant function because it's a horizontal line. This one has a V, that's absolute value. This one is parabola shaped, so that is a quadratic. This one looks like a straight line, but notice it has a hole right here. Remember, straight lines that have holes are considered rational. And that is one that students miss a lot, so be real careful right there. For this one, it has a definite starting point, goes forever. It's a square root function because it's got that square root shape. This one is linear through the origin, so that again, We could say it's linear, or we could say direct variation. And remember, if it's matching, I will only give you one of the choices, and you'll have to pick which one. So if it was matching, I would not give you both linear and direct variation for this one to choose from. You would have to choose one or the other. Only one of them would be available in the choices. This one has two curves. It's going in opposite directions, so that tells me it's got to be an odd exponent or to an odd power. This one is cubic. This has three curves. It's got to be an x to the fourth function. They're both going up, so that tells us it's an even power. So this one would be quartic. And then this one. Now, some people might miss this one and say that it's inverse or indirect variation, but remember, if it's indirect variation or inverse variation, the asymptotes have to be on the x and y axes. These asymptotes look like they're at x equals 1 and y equals 1. Plus there's a hole right here. So this one would have to be rational. You could not choose inverse variation. So rational for this one would be the only choice. For these, notice the x equals 0 and y equals 0 lines, the axes are your asymptotes. So this one would be inverse variation or indirect variation. Or you could say that that is rational. It could be either one if it's fill in the blank. For this one, that would be rational. It's got an asymptote here and here. So that one's rational. For this one, it does look like it goes forever in this direction. It goes forever in this direction. That one would be a logarithmic function. This one starts gradual and then gets very big very quickly. That would be exponential. And this one has pieces that are not attached. That's a piecewise function. The next thing we have to do is determine which equation would be the best choice for a line or curve of best fit. And our curves of best fit, we could use, well, first linear, y equals mx plus b. We could use curves, which would be quadratic. We could possibly have logarithmic or exponential functions. We could have cubic functions. It just depends on what trend the data is showing. Now for this one, I can tell that that is going to be a pretty strong positive correlation. Okay, so that's going to be a linear equation with a positive slope. So if we're talking about y equals mx plus b, then don't we know that our slope has to be positive? So anything over here that has a negative slope we can throw out. Well, we can throw out a and we can throw out b. So we know that it's got to be one of these. So we have to determine which of these would be best. Now, if I were to draw a line here, it does look like it would probably go through about 6. So my y-intercept would be at about 6. Well, we can't distinguish here which one that would be. The only thing we have to distinguish is the slopes. So if you think about it, let's look at a slope of 1/3 and then let's look at a slope of 3. So if I have a point right here, a slope of 1/3, if I go up 1, right 3, it's going to look something like that. And if you look at that, that's a gradual slope. It looks like it would be a kind of parallel to this one, right? So I would say that's probably the right answer. I'm going to go ahead and circle it, but let's double check what a slope of 3 would look like. So if I'm going to put a slope of 3 in there, I'll start right here, and that means I go up 3, right 1. And so if I draw my slope through those 2 points, it's a very steep slope, so that's nowhere near parallel to that data set. So that shows me that C would be the best answer here. Omar conducted an experiment in which he recorded the number of seconds groups of people took to line up in alphabetical order. His results are displayed in the scatter plot below. Choose the equation closest to the line of best fit for the graph. In this one, they've already drawn the line of best fit. And so if you look at that line of best fit and try to determine which of those equations would be the best. First of all, that's a positive slope. So we can throw out A right off the bat. There's no way the slope of this is going to be a -6 because that would have to be in this direction. All of these have the same slope, so we're going to have to determine which of these would be the best y-intercept. Positive 120 would be right here, right? It's very obvious that that thing is not going to cross at positive 120, so I can get rid of that. If you do negative 40 would be down here somewhere. It looks to me like it's pretty definitely not going to be this low, so I'm going to get rid of B. And you might argue that 20 is right here and it looks like it's going below that, and that's true, but they said pick the best answer, so choose the equation closest to the line of best fit. This would definitely be the one closest to the line of best fit. And then sometimes they might ask you to answer some questions based on that equation, but usually it's just going to be a matter of picking which one's the best answer. The next thing we're going to do is learn how to write equations when you're given information in a chart. I would suggest that you pause the video, write down that data, and then that you do this along with me in Desmos. It says a linear function is not the only function model for a set of ordered pairs. Sometimes a curve of best fit, for example, a quadratic function, may be a better model for some data than a linear function. One way to determine which is best is to eyeball the scatter plot to see if the data points resemble a line or a curve. If you have data points that look something like this, well, I would say that's got a pretty strong positive correlation, and I would be able to draw a line of best fit through there. So if I put this data in Desmos and the ordered pairs looked something like this, then I would know that a linear model would be the best model to use, okay? And so the linear model, we did this back, I think, in Unit 1 or 2, where we had to put in the table first and put the data in, and then underneath that in the next box, we had to put in y1 tilde mx1 plus b. And remember, we had to have the x1, y1 in our equation of the form y equals mx plus b. We use a tilde. That's kind of the symbol to tell Desmos we want it to generate an equation for us. If the data turns out to be linear, this is what we would put into Desmos to generate our equation. And then remember, once we did that, it would underneath give us a bunch of data for a and m and b and all these different points. But if you don't put the y1, x1, and you just put y and x, it will not work. So you have to have the y1, x1, and you have to have the tilde. If you put an equals, it will not work. You'll get an error message. Okay, so this is the equation you put in when the data looks linear. Now, what happens if the data doesn't look linear, but it looks like a curve? So let's suppose your data looks like this. Well, if I had data that looked like that, that to me looks like it would be a quadratic curve or a parabola. Now let's think back to what a parabola function would look like if we kind of put it in as something like this and ask Desmos to generate our function. We still need the x1 and the y1, but this time we would have y1 tilde. And remember, if it's a quadratic function, it would be an x squared function. So it wasn't the standard form of a quadratic, y equals ax squared plus bx plus c. So that's what we would write. Instead of y, though, we're going to put y1, and instead of x, we're going to put x1. So we would have y1 tilde equals ax1 squared plus bx1 plus c. So if our data looks like a quadratic, whether it's facing up or down, this is the equation we would put in to try to generate our quadratic function. So the next thing I'm going to do is go into Desmos, and I'm going to put this data in, and then we're going to look at the data to determine whether it's quadratic or linear, and then we're going to put the equation in and generate our equation. So I'm going to go into Desmos, and we're going to put this data in, and we're going to determine which of these, or which type of equation it would be, and which of these functions that we would put in. So remember, when you're in Desmos, to get the table, you hit the plus button, you go down here to table, that'll put a table in, and I'm just going to put the information, and after each one, I'm going to hit return, and then I'm going to just kind of drag my graph around and see if I can find it. Now, it looks like it must be way up there, and if you think about it, your y values, they don't begin until 88. So it's going to be way up there. So if I hit the minus button, notice my graph is getting a little bit smaller so that I can see what they are. Let's zoom in so we can really see what these ordered pairs are doing. For this one, I would say you could do either linear or quadratic. It does have a bit of a curve to the points if these are our ordered pairs, but you could also consider that a linear model as well. So they would have to be a little more specific with this one. So if they ask us to be or to find the curve. Let's go back and read. What did it ask for? So it just says the best thing to do is to eyeball the graph. It doesn't ask us to do one or the other. Well, that's good news. So I would say for this one, I would use a line of best fit. So let's put that in here. Let's go to the next line, and we're going to type in y1 tilde, and the tilde button is shift, or the button to the left of 1. And then that's mx1 plus b. And when I do that, notice it gives me a bunch of stuff down here. And so if I want a linear equation, I would write y equals, my m value is negative 4.98. So they might even have a negative 5x, plus b here is about 300. So I would guess that if it was a multiple choice, they would probably give you something like y equals negative 5x plus 300. And that would be a fine answer to use. Sometimes they may be specific and ask you to round to a specific decimal place. In that case, just read the directions and do what they ask you to do. In this one, consider the two sets of ordered pairs below. One table represents the perimeter of a rectangle with dimensions of x units and x plus 4 units, and the other represents the area of the same rectangle. Which should be modeled by a linear function and which should be modeled by a quadratic function? If you're looking at this, for this one, those look pretty straight to me. So I would say that would be the one that needs to be linear, and this one would be the one that needs to be quadratic. And then down here I'm asking you for the equation. So what I would do is I would go into Desmos and I would do this in the Desmos calculator. So you might want to pause the video, write them down, then go into Desmos and do this with me. So looking at Desmos for that first one, I've put in my data here, and then I generated the equation. Remember, it's y1 tilde mx1 plus b. And then down here, I've got my m is 4, my b is 8. You probably could have done this without Desmos, but it's good to do one on here. There's my basic graph. Here is my equation. And if I go back in here to the notebook, there is my equation for the first example. For the second example, I'm going to do the same thing. All right, for the second one, I put the data into Desmos. I've got that graph right here, and you can see that that is a pretty good parabola going through those points. I put in the second box, y sub 1 tilde ax sub 1 squared plus bx sub 1 plus c, and that gave me a, b, and c values. A is 1, b is 4, and c, let's see, that 2.2433 times 10 to the negative 15. Now, if you think about that, scientific notation, that number means we're going to move this decimal 15 places to the left. So for this, I would say that number is so close to 0, you don't even need to put it in your answer. Because even if we round it to 3 or 4 decimal places, it will still be rounding to 0. So for my answer, I would say that this data has an answer of y equals 1x squared, or just x squared, plus 4x. And then the c would be plus 0, so you don't need to put that down. So I'll go back into the notebook, and that's my equation for this set of data. A company began to produce an environmentally safe household cleaner in 2004. The table shows the number of units of product sold over the first 7 years it was on the market. Find the best fitting quadratic model for the sales of the product and explain your answer. They're telling you it's quadratic, so that means you know in Desmos you're going to put y1 tilde ax1 squared plus bx1 plus c. So you're going to go into Desmos, write down this data. Now, one thing I will tell you here, they're telling you for 2004 you're going to put 0 for your x value. For 2005 that's year 1, 2006 is year 2, and so on. So these would be the number of years since 2004 is what they're putting in the graph. That makes it a little bit easier to generate your equation. So go into Desmos, do that, and see if you get the same answer that I get. So go ahead and pause the video. Okay, so here's what I put into Desmos. I've got my table here. They told us to generate a quadratic model, so that would be the y1 tilde ax1 squared plus bx1 plus c. And I can get my a, b, and c values here. My equation is going to be y equals 0.76, I'll say 0.762x squared minus 0.5x plus 0.881. The manager of a large bookstore counts the number of books that are sold each hour since the store is opened. For example, since the store opens at 8 a.m., she will record the number of books sold from 8 a.m. to 9 a.m. as the number sold in the first hour. The table below shows some of her data. So hours since opening and number of books. I just wanted to make sure you saw one where the table was sideways instead of up and down. And understand that these values on top would be your x values. These values on bottom are your y values. Some students get confused about that, so I just wanted to make sure I showed you one like this. It says determine if a linear or quadratic model would be best, and then find the equation for that model. So go ahead, pause the video, see if you can get this one on your own. Put these numbers in Desmos. You determine whether a curve or a line of best fit would be the best answer, and then find that answer, and we'll come back and check it in just a few minutes. Okay, so I got that a quadratic model would be best. When you look at the graph, notice the graph went in a negative direction, so we know our x squared coefficient is going to be a negative number. And you can see where the line goes through the data points, so definitely a quadratic model is the best one. I rounded everything to 3 decimal places. You could round to 2 if you wanted to. It doesn't matter. They will be specific in the directions, or it will be multiple choice, and you'll just do what the answer choices indicate. So going back into the notebook, when I round those answers, I got y equals negative 0.424 x squared plus 8.161x plus 0.029. Okay, and sometimes they're just going to give you data sets and ask you which type of regression would be the best. And so this is really similar to how we started this section by identifying what type of function you have here. So with this one, I would say that would be a linear correlation. With the second one, notice it has two curves going up and down in opposite directions. That is a cubic function, so that would be the best model. This one I would say is exponential. It goes up toward the left exponentially. This one right here, they've drawn the curve in there for you. That's another cubic. This one has no correlation. I can't tell what line would be the best fit for that. So no correlation for this one. For this one, looks like that one is going up exponentially again. So I would say that's an exponential equation. This one looks pretty definitely like a quadratic curve. This one is very much a linear equation. And this one, if they ask you to do one in this section, you can't assume it goes forever. The data is going to go forever in that trend. So that would be a logarithmic function. So that's it for the section. Most of it's review, just kind of putting some things together.